All right, so now we'll continue with branch prediction. What we are essentially running into in the next, basically in the next set of problems we're going to discuss is what we call control dependent. What do you mean by control dependent? So let's say you write a code like this. If A equals 0, do something, otherwise do something else. Or you have a loop, right? And we use it all the time. I mean, how many people write a program without a loop, right? It does exist. You can use recursion, you can use functional programming, but generally, I mean, loops and branches are useful. The thing is, in your processor, how we can handle branch? Because in a pipeline design, right? Somehow I need this guy, the program counter. Somehow I need the program counter to point to the correct line, right? But let's say I have an if else. Do I point here or do I point here? All right. How do I make sure I update the program counter correctly? So there are multiple ways to handle control dependence. You can start the pipeline. You can guess. You can do the educated guess. We'll go through some of these options today. We'll dive into a basically much deeper way to do the educated guess in the third half of this class today. And we can do many other things. For example, our lab, the MIPS R4000 would do delay branching or the branch delay slot. We'll talk about that as well. You can do something else like a GPU, try to do like fine-grained multi-threading. You can also use predicated execution. So basically, the GPU kind of use these two bullet points. You can also do multi-path execution. And here is the simplest solution. Again, sorry about this bug. Is a program counter. All right, folks, is a program counter. Easy. Okay. Okay, so let's say I have instruction 1 here, instruction 2 here, instruction 3 here. And let's just assume that this is a branch. What does it mean to be a branch instruction? What does that mean? It can basically mean that, let's say I have a code like this. If something, do this, code block A, else you run code block B, right? So depending on my condition, my program counter should either point to A or B. All right, with me so far? Depending on the condition of my if else, program counter should pick, do I go to A or B? มีคำถามไหมครับ ก็คือถ้าเรามี if else อะเราต้องรู้ว่าเราต้องไปรันใน if หรือรันใน else แล้วไอ้ตัวที่ต้องรันอะตัวที่จะชี้อะมันคือโปรแกรม counter นะครับ All right, okay, so now let's say you have no problems here. If I have to start the pipeline, my first question is, when do I know the condition? My first question is, when do I know whether I have to go to A or B? What stage? Is it in decode or is it in execute? Even with data forwarding, let's say I have the most aggressive way to do data forwarding. How do I resolve this guy? I have to be in the execute, right? Because that's an actual operation that's done in the ALU. The decoder has no way to tell. So basically, if instruction 2 is a branch, I cannot move instruction 3, right? If I want to style, I have to wait. I cannot even fetch, right? Because depending on the result of my if else, I might have to go to A or B. This still have the possibility of pointing at A or B, and you don't know until this guy move here. So instruction 2 has to be in the execute. Instruction 2 has to be in the execute at minimum before instruction 3 can start moving. So at least for this particular question, you have to stall for one cycle, right? One cycle. Now here's a even bigger problem, even bigger problem. How can I tell, is this a branch or not? When can I tell what is the type of my instruction? How can I tell if instruction 1 is a branch or not? Again, so to repeat this problem, right? Decode is when I will know the type of my instruction. I cannot know in the fetch. All right. So let's say I fetch instruction 1 into my pipeline. With this particular scenario, I fetch instruction 1 in, right? In the next cycle, in the pipeline design, what should happen? In the pipeline design, what should happen? I fetch instruction 1 then go to the decode stage, right? What do I fetch next? Can I fetch instruction 2? In reality, if you just want to start a pipeline, you cannot even fetch instruction 2 because when you move instruction 1 into the decode, I don't know the type until decode, so you cannot fetch instruction 2. You need to move instruction 1 until you finish the decode. That's when you know, okay, if it's not a branch, I can do instruction 2. All right. So let me translate this in Thai just to clarify again. ก็คือสมมุติผมมี instruction 1 มาเนี่ยอยู่ใน fetch unit แล้วผมจะขยับ pipeline ผมก็คือ instruction 1 ก็จะวิ่งไปที่ decode ใช่ไหมฮะ instruction 1 วิ่งไปที่ decode ปัญหาเนี่ยคือ fetch unit ด้วยความที่ตอนที่เรามี instruction 1 อยู่ใน fetch เราไม่รู้ด้วยซ้ำว่าไอ้นี่คือ branch หรือมันไม่ใช่ branch เพราะว่าถ้ามันเป็น branch มันแปลว่าโปรแกรม counter มันอาจจะเป็นค่าอะไรก็ได้แต่ถ้ามันไม่ใช่ branch ก็คือบรรทัดต่อไปได้แน่ๆนึกออกใช่ไหมฮะแต่ด้วยความที่เราไม่รู้เราก็ต้องรอจนกว่าจะรู้การที่รอจนกว่าจะรู้คือ instruction 1 ต้องวิ่งไปที่ decode ก่อนเพื่อที่มันจะรู้ว่าอันนี้มัน branch หรือเปล่าถ้ามันไม่ใช่ branch ตอนเนี้ย decode มี instruction 1 อยู่ถ้ามันไม่ใช่ branch fetch จะเป็น bubble เพราะเรา fetch ไม่ได้แต่ว่า cycle ต่อไปเราจะ fetch ได้แล้วเพราะเรารู้มันไม่ใช่ branch ถ้ามันเป็น branch แล้วมันมี condition อย่าง if else อันเนี้ยก็ยัง fetch ไม่ได้อยู่ต้องรอ instruction 1 วิ่งเข้าไปที่ execute แล้วเราถึงค่อย fetch ได้ก็จะทำให้ stall ยาวนะครับปัญหาของอันนี้ก็คือเราต้อง stall เราเรียกว่า every after cycle ทุก instruction เรา stall 1 ครั้งแน่ๆเพราะว่าเราไม่รู้ด้วยซ้ำว่าไอ้นี่ instruction เนี้ยมันเป็น branch หรือเปล่ามีคำถามไหมครับเคลียร์หรือเปล่า So let's say I have these program, right? I fetch instruction 1. I don't know the type until I decode. Because I don't know the type until decode, and this is execute, memory, and write back, all right? Because I don't know the type until I decode, right? I cannot fetch. Because I don't know the program counter, I cannot update the program counter, so I have to fetch here, decode, execute, memory, and write back. And here, because we want to do branch if not equal to, right? B and E is branch if not equal, which means that I don't know the condition of my branch. I don't know what to do with my branch until execute, which means that I have to delay the fetch even further. And again, because I have to process the XOR instruction, right? I don't know that's an XOR until here, so I have to delay again. Fetch, decode, execute, memory, and write back. So as you can see here, you also always have to insert the bubble whenever you have to decode here and here. Then you have to do the bubble here and here because you don't know the condition of your branch. So you have to insert one more bubble. And you're wasting cycle, you're wasting your CPU by not doing this earlier. But you cannot because you don't know you have control dependence. This is what we call control dependence. Control dependence basically means that I don't know what should the program counter be until something happened. It basically means I don't know what's my program counter. And I cannot really update the program counter. So I have to stall until the program counter can take the right value. Okay. มีคำถามไหมคะสำหรับสไลด์นี้ All right. Now, the next thing we can do is blindly guess. Okay. So the next thing we can do is blindly guess. So for example, we can always guess that the next instruction is not a branch. That way I will always fetch after someone decodes something, I fetch all the time. So you get rid of that delay, right? And if I fetch the wrong instruction, I just throw it away and fetch it again. So I can do blindly guessing, right? I'll just now blindly guess. When I guess, there can be two outcomes. You are either right or wrong, right? It's like a true or false exam. You are either right or wrong. So you just guess, okay? So assume that you're always right. Assume that you're always guessing correctly. This is what happened. So I'll do fetch, decode, execute, memory, and write back. Now, the first line comes in. You guess that, hey, let's assume that's not a branch instruction. So you guess correctly. Fetch, decode, execute, memory, and write back. Now you go to XOR, and you guess that the branch not equal. Somehow you guess correctly. You're a magician. You know what's going to happen. You guess to fetch the XOR. So you can do fetch, decode, execute, memory, and write back. Then again, you guess that it's not a branch instruction, right? Memory and write back. So this is what happened. You guessed correctly, fully pipeline, right? And really good performance. So if you do a good job at guessing, you're going to perform well. Now, what if you have a wrong prediction? Let's say you guess this correctly, but you always say, hey, the next instruction is not going to be a branch. So you're going to guess correctly here, here, here. And then for this guy, it's like, oh, I'm wrong, right? So you fetch, fetch, decode, execute, memory, and write back. This guy you fetch, right? Because you guess that I have to run instruction 2. You decode them. You execute, memory, and write back. Then you guess that, hey, I have to fetch something. And you don't know the result of your branch not equal until here, right? So you decode here, and then you realize that you're wrong. Then you realize that you're fetching the wrong instruction. In that case, you have to refetch. So you go back to the right instruction and you do it all over again. So in this case, you stall for 2 more cycles because every time you make the wrong prediction, you're basically wasting 2 cycles. Quick recap for this slide in Thai, just to make sure we are all on the same page, right? ก็คือสมมุติว่าถ้าเราบอกว่าเราไม่รู้ว่าโปรแกรมเคาน์เตอร์มันต้องมีค่าอะไรกันแน่เราก็ตีตามไปเลยทุกครั้งที่ต้องเฟทก็เฟทบรรทัดต่อไปก่อนเพราะว่าโปรแกรมส่วนมากมันไม่ได้ if else ตลอดเวลาเนาะก็ make sense ที่จะเฟทบรรทัดต่อไปเพราะฉะนั้น instruction 2 มาถึงปั๊บไอ้ branch not equal ก็แบบมันก็บรรทัดต่อไปก็ถูกแล้วกรณีที่มันเดาแล้วเราผิดก็คือ fetch บรรทัดต่อไปแล้วอย่าง branch not equal เนี่ยสมมุติว่ามันเดาผิด แล้วมัน fetch ไปแล้วมัน decode ไปแล้วเพราะว่าเราไม่รู้ว่ามันจะเดาถูกหรือเดาผิดจนกว่าเราจะ evaluate ไอ้ not equal เนี่ยมัน not equal จริงหรือเปล่าการที่ evaluate ว่า not equal มันจริงหรือไม่จริงอ่ะมันจะอยู่ใน execute เพราะว่า ALU ต้องเป็นคนคิดนะครับ ALU เป็นคนตัดสินว่าไอ้ not equal เนี่ยมัน true หรือ false เนาะก็ถ้าเราอยู่ใน execute ก็แปลว่าเรา fetch กับ decode instruction ก่อนหน้าไปแล้ว2 อันนึงอยู่ใน decode อีกอันหนึ่งอยู่ใน fetch เราก็ต้องบอกว่าเรา fetch ผิดอันปาทิ้งให้หมดแล้วก็ fetch อันที่ถูกต้องนะครับเราก็จะเขาเรียกว่า squash คือปา instruction ที่แบบไปผิดทางออกแล้วก็ให้โปรแกรม counter ชี้ไปที่ถูกต้องแล้วก็ fetch ใหม่นะครับมีคำถามหรือเปล่าถามภาษาไทยได้นะครับ Basically, the summary here is, let's say you do the 5-stage pipeline. If you make the wrong prediction, you waste 2 cycles fetching wrong instruction. Then you can squash, which means you throw it away. Then you refetch the correct instruction. All right. Now, today we can focus on this. Let's say I give you an exam, and it's a true-false question. It's a true-false question. What should be your strategy? You always, right, try to pick the right answer. And if you don't know the answer, what do? You're going to try to do educated guess, right? And hopefully, educated guess is hopefully slightly better, or if not, much better than blindly guessing. All right? So what information do we need in order to guess the branch? First of all, we need to figure out if this is a branch or not. If it's not a branch, you run the next line. If it's a branch, you figure out the outcome of the branch. Do I need to take the branch? Let's say I have an if-else, right? I have an if-else statement. Do I go to the if or do I go to the else? So that's the second bullet point. Do I go to the if or else? Then, if I have to go to the else, which is jump in your code, what line is that? What line is that? We call this the target address. The target address. If I don't go to the next line, what line am I going to? So here's if I am not going to the next line, what line I am going to? Okay, with me so far. We need to be able to make these 3 predictions. And it turns out that there are something here that are really, really easy. But before we go there, what's the simplest form of guessing? For example, you can always predict that whenever I see a branch, I will not take the branch. I will go to PC plus 4. I'll go to the next line. Whenever I see a branch, I will go to the next line. That's a really simple way to guess, right? You see true or false question. Every time you see true false question, always answer false. Because, I don't know, maybe this particular person that make the exam statistically always have whenever it's true false, always it's a false answer. So that can be the simplest form of guessing. I mean, why this might work well, for example, right? If I have an if else, right? It might be the case that if happen more than else, right? Can we do something else to help? For example, you might also notice that for loop, right? When you have a loop, what usually happens is when you run the code from top down here down to the end of your loop, right? Most of the time you go back and loop around. Most of the time you always jump back, right? It's only one time that you exit the loop and go to the next line, right? So something that you can do is maybe you can use a compiler. And if you know that the machine always predict certain things, you then optimize the compiler to change your assembly to make it more friendly toward the hardware. So that's the solution proposed in like PLDI 1990s. The downside of this is, again, is too simple in most cases. It might not work that well. And when you mispredict, you insert two bubbles as you saw earlier. So let's assume that in your code, 10% is if else. 10% is control for like branch or jump. And then 80% of the times are taken, and you always always predict not taken, right? It means that let's say you have to run 100 instruction. It means that 10%, which is 10 instruction, is a branch, right? 80% of the time is a taken branch, and you always predict you're not going to take a branch, so you're almost always wrong. So out of this, 8 are wrong, 2 are correct, right? So these 8 wrong outcomes, you insert 2 bubble each, so this is 16 cycles, right? So from 100 instruction, you're gonna finish this in 116 cycle. Your CPI is essentially 1.16 instead of 1. So you're basically performing 15% worse. Now, if you predict correctly, most of the time, in this case, again, 100 instruction, right? 10% are taken, so 90% of the time you're correct. So use 9 correct, and 1 wrong, right? Out of the 10 branch, so this is 2 cycles. Your CPI is 102 over 100, so it's not too bad. It's only 2% worse. Okay. So this is the cause of branch misprediction. Your goal is to make a better prediction, because as you can see here, between 16% worse and 2% worse is a big gap. I want to be able to predict, do I go into the if or do I go into the else? All right. Now, I'll go back to this slide. There are 3 things we need to figure out. First, is that a branch, right? So let me ask you this question. Let's say I have a program A. All right. When I run this program, I basically compile into assembly, right? And let's say whenever I see program counter of, I don't know, 24, right? It's an if else. Then when I run and go to line number 140, again, that's a loop, right? And that's my program. And I keep running this program. Every time I go to line 24, what do I expect? I just see if else again, right? That if else instruction, it doesn't move around. It stays there because that's your program. The program is a static thing. So every time you see program counter of 24, it means that, hey, that's a branch. Again, with the same program, when you see the program counter value 140, it's going to be a loop. Otherwise, it's not a branch. Let's say your program counter point to 28, not a branch. When it's 32, again, not a branch, right? So quick recap in Thai คือโปรแกรมเราเวลาเราคอมไพล์เสร็จนะครับไอ้ที่อยู่ของมันไอ้ที่โปรแกรมเคาน์เตอร์มันชี้อยู่เวลาเรารันif else มันจะอยู่บรรทัดเดิมมันไม่ move ไปไหนอยู่แล้วเพราะว่าเราไม่สามารถเขียนโปรแกรมให้มันแบบบรรทัดมันขยับที่ได้เฮ้ยคือมันไม่ขยับนะครับทุกคนบรรทัดมันไม่ขยับที่เพราะฉะนั้นถ้า if else มันอยู่ตรงไหนมันจะอยู่ตรงนั้นไปเรื่อยๆเพราะฉะนั้นเราก็บอกได้ว่าถ้าเราเคยเจอโปรแกรมเคาน์เตอร์อย่างตัวอย่างเนี้ยก็คือโปรแกรมเคาน์เตอร์ที่24แล้วเราบอกว่าอันนั้นเป็น branch พอโปรแกรมเคาน์เตอร์กลับมาที่ค่า24อีกรอบเรารู้เลยว่าไอ้นั่น branch ชัวร์ๆนะครับไอ้นั่น branch ชัวร์ๆทุกคนหา solution กัน so if this is our observation what can we do to predict whether an instruction is a branch or not? We can store the location of the branch that you saw, right? Basically, the instruction doesn't change itself. The program doesn't modify itself when it's inside the main memory, is there. So one thing you can do is, the branch instructions stay at the same place. Whenever you see the program counter that point to the branch instruction you've seen before, you know for sure that's a branch. So that's the first thing, right? I can use the program counter value to predict whether it's a branch or not a branch. I can use it for sure because if I see the program counter and I know that the last time I see this guy is a branch, I will know the next time I see it, it's a branch as well. So one thing I can do is to put the program counter value in the set. Whenever I see the program counter value that is a branch of my program, I put that value in a set. Say, hey, whenever I see that anything that is appearing on this set, it means it's a branch instruction. Now, the next thing I want to figure out, and the next easiest thing is the target address, right? Where do I jump to? Let's say I have if else, right? If you have to branch, you need to measure from this line, you need to then jump to here. And again, the same observation, you don't modify the program. So almost always, you always jump back to where you were. Most branch are jumping back to the same target address. So we can also store the possible target in a large buffer, right? So I can store this. I can store a pair of program counter and the target. And basically, in a high level, I want to store just that. I have a set that consists of a pair of program counter and the target. Whenever I see the new program counter value, I search the set. If I find something in the set, it means that's a branch, and I know where do you branch to. So my set's going to look like PC1, target 1, PC2, target 2, PC3, target 3, ... So that's what my set is going to look like. Whenever I see a new program counter, I search the set and see if there's anything in the set. If there's anything in the set, it means that that's a branch instruction, which means I then basically need to go to the target. All right. How do we implement this in hardware? Here's a solution. I will use a big buffer that looks like a table. Sometimes we call this a branch target address cache. Sometimes, in most cases, if you read textbook, it will read the branch target buffer. All right. So the solution to this is to use the branch target buffer. It records the target of the previous branch from the same program counter. So based on the program counter value, you produce a target. All right. So the structure is this. You have the program counter. The program counter would first check with two things. The first entity is called the direction predictor. We are not going to talk about this guy yet, but the branch target buffer will store and use the program counter as a key. Are you guys familiar with the concept of a map where you have a key, it produces a value, the map? เคยใช้ map กันใช่ไหมครับ map ที่มันจะมีเอา key ไว้ search แล้วก็ถ้าเรา search เข้าไปแล้วเจอมันจะได้ value อ่ะหน้าตาเหมือนกัน มันจะเป็น table ใหญ่ๆ แล้วทำงานเหมือน map. So this branch target buffer acts like a map. I use the program counter as the key. I search the branch target buffer. There are two possible outcomes. I find the key. it means that that's a branch and it gives me the value, which is the target. Where do I branch to? The second outcome is I cannot find the key. If I cannot find the key, that's not a branch. That's not a branch, so I know I go to PC plus 4. All right. So let's say it's a branch. So if you found your key, right? So if you found your key, it means it's a branch. The next thing you have to predict is, okay, yes, fine, it's a branch. It's an if else. Do I take the branch or do I go to the next line? So the next thing is the direction predictor will also then predict, do I go to the next line, which is PC plus 4. Basically, PC plus the instruction size, that's the next line. So this is the next line. Or this is a branch. Basically, you jump somewhere to the target address. All right. And the next PC, the next value for your PC is going to either be the next line or the target address based on the outcome of your branch target buffer and the direction predictor. รีแคปอีกนิดนึงนะครับภาษาไทยก็คือเรามีโปรแกรมเคาน์เตอร์อย่างดีไซน์เราอยู่แล้ววิธีการที่เราจะ predict ว่าไอ้โปรแกรมเคาน์เตอร์ค่าของมันใน instruction ต่อไปอ่ะมันจะเป็นอะไรกันแน่มันจะสามารถทำอย่างนี้ได้คือเราโปรแกรมเคาน์เตอร์ไปเป็นคีย์ใน branch target buffer branch target buffer มันจะให้เอาคำได้2แบบก็คือหาไม่เจอถ้าหาไม่เจอจบโอเคแปลว่ามันไม่ใช่ branch เราก็ไปที่ PC plus 4ก็คือไปบรรทัดต่อไปแหละเพราะว่ามันไม่ใช่ branch ถ้ามันเจอแปลว่าอันนี้คือ branch ถ้ามันคือ branch สเต็ปต่อไปคือต้องดูว่าเราจะ take ไอ้ branch หรือเปล่าถ้า take branch ก็คือไปที่ target address ถ้าไม่ take branch แปลว่าเรา predict และเราเดาแล้วเราคิดว่าเอ้ย branch อันเนี้ยเราไม่เข้าไปแน่ๆเราจะไปบรรทัดต่อไปเราก็จะให้ next PC เป็น PC plus plus 4ก็คือ instruction size นั่นแหละครับก็คือไปบรรทัดต่อไปมีคำถามไหมครับ All right, so now we are done with these two things. I can now figure out if the instruction is a branch. I can now figure out if it's a branch, what's the target? Using the branch target buffer. The only remaining question is, well, let's say it's a branch. Do I take the branch or not take the branch, right? How do I determine the direction of the branch? So to predict, right, there are multiple papers and research that looks into what's the best way to predict the outcome of your branch. Even now, there's still quite a bit of the literature into like, how do we do this? One thing you can do is called static branch prediction, which is I use a compiler. Basically, hardware do nothing. And then guess like always taken, always not taken. Then I rely on the compiler. Then if the compiler knows that hardware is always taking the branch or not taking the branch, then I optimize my code, my assembly to be more friendly toward one of them. All right. Another possibility is that there were another idea called BTFN. If it's a backward branch, these are loops. Usually you implement a backward, like you implement loop in assembly using a backward branch because your code is gonna go down, right? And then you go back up. So that we call this a backward branch. You always go back up. You jump back loop, jump back loop, jump back loop. So that's a backward branch. And if it's a loop, you always, most of the time, you are taking the branch. So taken if it's a backward branch, not taken if it's a forward branch, because if it's a if else, for example, in many cases, you go to the if, right? Then you would go to the forward branch. You can also profile. Profile means that I run my program for a bit and look at the history, and then I compile my code based on what I saw. I might be running my program for like 1 minute and look at the history, and then the compiler would reshuffle your program to be more friendly toward one thing or another. The majority of the class today, we will talk about what actually happened in the CPU. This is dynamic branch prediction. It's runtime branch prediction. You run the program, it tries to build the history, something in the hardware, it then try to predict, do I take the branch or not take the branch? All right. The simplest form of runtime predictor is the last time prediction. You can also kind of expand this a bit, and then you can do like 2-level prediction, which is like the third half of this class today, and more, right? Again, I talked about TFN already. If you have a loop, in this case, you take the branch, you go through the loop. Otherwise, you go to PC+4. You can also use profiling or pragma. Pragma is something the programmer can use. These are keywords that you can hit to the hardware. For example, you can kind of make the new API as a likely, if likely X. It means that this if is likely, then the hardware can kind of follow that and know the outcome, hopefully, of the branch. Pragma can be useful for many other purposes, like can I run the loop in parallel, like many implementation of OpenMP kind of like rely on Pragma. You can send message to the system, and if you have bugs in your Pragma syntax, it doesn't cause compilation error. It will still run without the Pragma. All right. Again, the meat of this class today is going to be on dynamic branch prediction. So the idea is I want to predict the branch using runtime information. Now we'll just start with the first bullet point, last time prediction. All right. Last time prediction works like this. The branch target buffer store 1 bit. What happened last time I saw this program counter? If I take the branch, I would predict that, well, this time I'll take the branch. If the last time I saw this branch, I do not take the branch, well, I'll not take the branch. This is simple. This is simple. Basically, I just predict based on what I saw, right? This bit will be 1 and 0 that correspond to the direction of that particular branch. What happened last time? Do I take the branch or not? So the state is as simple as this. If I predict not, let's say I start with here, predict taken, and the actual outcome is not taken, the next time I'll predict not taken. If I predict taken, then the actual outcome is taken, I'll stay here and predict taken again. And the same logic applies for predict not taken. For example, let's say you have a branch that go with this. I take the branch 5 times in the beginning, then I don't take the branch, then I take the branch again at the end, right? Your prediction is going to be correct. Well, let's assume it's initially started predict taken, so you're going to be correct for the first 5 times. Then when you go to not taken, you're not correct. But because the last time you saw is not taken, so you're going to predict not taken again. So you're going to be correcting 3 more times and then incorrect here. The last time predictor really suck, to be honest. It's really bad. Oh, it's really good, for example, if your outcome is really predictable, like over here, it's like always taken, right? If it stays the same all the time, you only mispredict once. But if your outcome alternate a lot like this, right? You're only going to be at 50% correct. Oh, actually, no, my bad. This is always incorrect, right? So the first one here, I mean, initially, because it's a taken, initially I said I predict taken, so this is correct. Just pure luck because I initialized my state to predict taken. Then not correct, not correct, not correct, not correct, not correct, not correct, not correct all the time. So this is going to approach 0%, right? So as you can see, this is, yeah, it's kind of okay. For the most part, it's better than nothing, right? But there are patterns that would break the last time predictor. And to implement this, right, one thing you can do, here you can see the branch target buffer at the bottom, right? The branch target buffer. The way you implement this, you have the program counter that break things down into tag and index. The tag is used as a key to search The index is used to kind of go to the row that you want to search. Then the tag would check, is the entry here? The history table is 1 bit. That either be 0 or 1. If it's a 1, it means I want to take the branch. I want to predict that this is a taken branch. If it's a 0, I predict not taken. And based on that, I would use the branch target buffer accordingly to update the next PC. All right. Translate this in Thai to make sure. ก็คือไอ้ last time predictor อะฮะมันทำงานง่ายๆมากๆเลยก็คือ รอบที่แล้วที่เราเจอ branch อันเนี้ยมันเทคหรือไม่เทคมันจะ predict อันนั้น มันจะเดาว่าถ้ารอบที่แล้วเป็นเรา take branch มันก็จะเดาว่าเรา take อีกแล้วกัน ถ้ารอบที่แล้วไม่ take branch เราก็จะ predict ว่างั้นไม่ take นะครับ วิธี implement อ่ะมันก็ง่ายๆก็คือว่าเราเอาโปรแกรม counter เป็น key เหมือนเดิมนะครับโปรแกรม counter เป็น key เหมือนเดิมเราจะใช้ส่วนหนึ่งของโปรแกรม counter มาดูว่าต้องไปแถวไหนอีกส่วนหนึ่งจะมาเช็คว่าเราเจอหรือเปล่านะครับถ้าแท็กตรงแปลว่าเจอคือเราจะแบ่งโปรแกรม counter เป็นสองตอนตอนแรกจะเป็นแบบว่าจะไปดูว่าจะไปที่แถวไหนเพื่อความที่จะเวลา search มันจะได้เร็วๆนะครับส่วนแท็กเนี่ยเป็นคีย์เอาไว้ดูว่าตรงหรือเปล่าคีย์ตรงแปลว่ามันเจอแล้วไอ้ history table เนี่ยก็คือจะเก็บแค่1 บิตถ้าบิตเนี้ยเป็น1แปลว่ารอบที่แล้วรอบที่แล้วที่เราเจอ branch อันเนี้ยมันเทคเพราะฉะนั้นมันก็จะบอกว่าเอ้ยรอบนี้ก็เทคละกันก็ไปที่ target address ถ้าบิตนี้เป็น0ก็แปลว่ารอบที่แล้วที่เรารันโค้ดเราสมมุติเรารันโปรแกรมอยู่รอบที่แล้วที่เราเจอ branch อันเนี้ยมันไม่ได้ take branch เราก็เลยเดาต่อว่างั้นครั้งนี้ก็ไม่ take branch ละกันก็มันก็จะไปที่ PC+4 นะครับ so that's the last time predictor which again yeah it's okay it's not too good it's not too bad all right can we improve this we can add one more bit for example I can use a 2-bit predictor this is a paper proposed in ISCA 1981 study branch prediction strategy, right? So the last time predictor would change the predicted direction from just one different outcome, a different outcome, which is not a good strategy, right? So the solution proposed in the paper is to add a hysteresis to the predictor at the state so they can store longer history. So it used 2-bit to track the history and prediction doesn't change with one single different outcome. Sometimes we call this bimodal prediction and here are the state. So you have, again, 2 bits. So you can predict taken for half of them, predict not taken for the other half. And the way you transition is, let's say you're in sometimes we call this a strongly taken. It means that I believe so strongly because I've seen taken branch all the time. I will keep predicting taken. So if I take a branch again, I'll stay at the same state. If I predict taken and I don't take a branch. Now you're in the weakly taken. The weakly taken state works almost the same way as the strongly taken, but it predict taken. It is still predict taken, but if you see taken again, you go back to strongly taken. If you see not taken, you now transition to the predict not taken. So again, if you are in the strongly taken, to finally predict not taken, you need to see 2 not taken branch. Because you want to have the weakly taken in as an intermediary so that you don't flip your answer right away. Right? Now, if you're in a weakly not taken, so there's a weakly not taken, and you see the taken branch, you go back to the predict taken, and the last state is a strongly not taken. Right? Again, quick recap in Thai ก็คือถ้าเราจะใส่อีก1 บิตเราจะสามารถใช้แบบว่าถ้าเรา predict taken อยู่เยอะๆแล้วเราเจอแบบ taken เยอะๆอย่างเงี้ยฮะใช่ก็คือเหมือนกับว่าสมมุติเราเจอ pattern แบบมัน take branch ตลอดเลยการที่เราจะเปลี่ยนใจว่าขอเดาว่าไม่ take ละกันเนี่ยก็จะต้องใช้ false prediction 2 รอบคือจะ transition ตัวเองไปอยู่ใน predict not taken เหมือนเวลาเราเดาแล้วแบบถ้าเรามั่นใจมากๆมันต้องตอบ true false อย่างนี้แล้วตอบ true ต่ออย่างเงี้ยเราก็จะเดาต่อก็ตอบ true ไปเรื่อยๆแล้วกันต้องเจอ false 2 รอบถึงจะเปลี่ยนใจงั้นเปลี่ยนใจแล้วไปตอบ false อะไรเงี้ยครับประมาณนั้นนะครับ so that's the 2-bit predictor with the saturation counter so you can use a counter in hardware to implement this and the performance is actually quite okay, right? So in this case, so let's say you initially is the predict taken in any predict strongly taken or weakly taken, you're going to be correct here, right? You're not going to be correct here. You're not going to be correct here because you need to convince yourself to go to the not taken, correct, and incorrect here, right? So this is basically 70% accuracy, right? Over here, you're going to get 90% accuracy. If you have the pattern that's really, really bad for 1-bit predictor, then let's say you're in the strongly taken, you're going to be correct here, incorrect here. Because you're always going to predict taken for here, right? So you're going to be 50% correct. You're improving the design. Now you're 50% correct, all right? So generally, if you do the analysis on a typical program, you will find that you're going to be about 85 to 90% accurate when you predict the outcome of your branch. About 85 to 90% accuracy. All right. So the question that you always should ask is this good enough? So because control flows happen a lot, you have a lot of if else, a lot of for loop, and you fetch, sometimes you don't know where do you jump to until after a lot of cycles because your pipeline is deeper, right? You're basically wasting a lot of instruction that you mispredict and you have to throw it away, right? So, sorry. So the conclusion is not good enough. I guess it's okay for the 1980s, but it's not good enough in 2023, right? So we are gonna then transition to a better design. Because it's a third of the class again, let's do a quick break. We'll come back at 11:10. If you have any questions, put it on the chat. When we come back, I'll go through the questions first, and we'll resume with the 2-level prediction. All right. Okay.